Well, greetings, friends. Welcome back. Welcome back to the sequence of training videos that I've set up for electronics engineering and electronics technology students to be able to do labs at home. There's a DC sequence where students can learn how to do their DC labs, and this is AC topic number 2 as part of the AC series of electronic experiments that students can do at home. This particular training video focuses its attention specifically on two products of interest. One is the PicoScope, number 2204A, and this will be in comparison with the FNIRSI, I guess that's pronounced FNIRSI, model 2C53P. Now, let me make it very clear that this is not a sponsored video. I'm not paid for recommending one versus the other. I purchased both of these machines outright to test and see how they would be appropriate for our students to be able to do AC experiments at home. So with that being said, let's go ahead and move forward. The welcoming screen shows the displays of both screens. The one on the left is the PicoScope, and the one on the right is the FNIRSI. And all right, so what is an oscilloscope and how does it differ from a voltmeter? Fundamentally, a digital multimeter, DMM, when you use it as a voltmeter, shows a digital value of the voltage quantity being measured at one point in time. An oscope is also a voltmeter. It's a voltmeter that graphically shows how voltage changes over a period of time. When you use it to measure DC. A voltmeter will show a fixed DC value if that voltage source is fixed. There is variable DC that you will encounter, and we'll talk about that in a separate training video. But as long as the DC voltage is fixed, then the digital multimeter will be able to show a fixed DC value. Now, to measure DC on an oscope, the oscope will display that DC quantity as a flat horizontal line. We'll show you that in a future training video as well. When used to measure AC, the voltmeter will show you the RMS form of the AC quantity, RMS root mean square. I discussed this in our AC topic number 1 YouTube that precedes this, what RMS is and how to calculate it. So when you measure AC, the voltmeter, your digital multimeter used as a voltmeter, will measure AC as a digital value, and it will measure it in a format known as RMS. So the RMS form of the AC is what the digital voltmeter will display. Now, when you're measuring AC, an oscope differs by showing you graphically the AC waveform. What happens is it shows you how the voltage changes over time. Visually on the screen, you can see the comparison of the two display screens, the digital multimeter on the far left, and then 3 different sample displays of oscope screens show voltages and how they change over some quantity of time. Digital multimeter used as an ammeter, because you can use a DMM as an ammeter to measure current. Now, when we're measuring AC, the digital multimeter will read the RMS form of the AC currents. So yes, you will be able to read amperes, milliamperes, microamperes, but not in peak format, but in RMS, which is, again, a calculated value, which we'll show you how to do later. An oscope is a glorified voltmeter. We don't typically use it to measure currents, so don't think about using a oscilloscope for measuring currents. Just use the digital multimeter as an ammeter to measure AC currents. Your AC Tech experiments at home. This is task number 1. So in task number 1 from my previous training video, AC topic number 1, you want to feel confident in being able to determine the quantities that are in the yellow box based on the display that is shown on the left-hand side of the screen. I am using, I believe this is Multisim, and in Multisim, as a simulator, I've got a signal generator. The signal generator box is covered by the yellow box, so you can't see what is being generated in terms of frequency. You can't see what's generated in terms of volt peak to peak or volt peak. That's covered. So it's your task to be able to read the waveform on the display and read the waveform on the display to determine the quantities of interest. And I showed you in AC topic number 1 video how to read an oscilloscope display. So if you don't recall, review the previous topic video and you'll get a good handle on this. But if you've been following the sequence of videos, this should be a piece of cake for you. So what are the objectives in the yellow box? You first need to determine something called period, which is the time for one cycle. Then you need to be able to determine frequency, which is the reciprocal of period. Then you need to be able to determine at various points, which I've marked with red lettering on the schematic and the nodes showing the specific points of interest, can you determine the voltage that would be measured at point A with respect to ground in both peak and RMS formats, and then at point B and then at point C respectively, just by reading the oscilloscope display. So let's see how we're going to progress with this and see if I can help you get started. Okay, we're not solving this for you, but this will hopefully guide you in the right direction. We are still solving the quantities in the yellow box, but we're going to start with period and frequency first. We won't dive right into the voltage values immediately. So based on the number of horizontal divisions for one cycle, you multiply the time base to determine something called the period, which is represented by the symbol capital T, and it's probably some quantity of milliseconds, microseconds, nanoseconds, some quantity of seconds. Then you got to remember that frequency is calculated as the reciprocal of period, and you should be able to calculate frequency. So what you ought to do now, see the stop sign on the lower right-hand corner, is truly stop the video, take a moment, calculate these quantities based on what you've learned previously, and very importantly, record legibly in your journal what you want to commit to. What are you going to commit to as being the count of number of divisions for one cycle? What you're going to commit to in writing, legible writing, for the period, and then write down what you commit to with respect to frequency. So pause the video. We will come back in a moment after your pause, and we will look at the solutions. Very important, you do not just go on to the next slide, okay? Don't cheat. You have to do the work. The whole point of the sequence of videos is hands-on learning, and so you need to do the hands-on calculation with the scientific calculator. Pause, and we'll be back in a moment. Okay, we're back, my friends, and hopefully you were able to get these quantities calculated. If you count the number of horizontal divisions for one cycle, back in the previous training video, AC topic number 1, I showed you that the big squares are called divisions, major divisions for these big squares, and then the little hash marks on the DC reference line are minor divisions. But you count the big squares, the big divisions, so you count 1 square, 2 square, 3, 4, 5 divisions for one cycle, and it's also defined what is one cycle in the previous training video. If you recall, can you speak it out loud? Is it in your journal? If you can't speak it out loud, if you cannot define what one cycle is, then you need to go back to your journal and reread it, rewrite it, because until you can speak it out loud to a classmate, to a prospective employer, if you can't verbalize, you're not going to be the one that's going to be hired, okay? So we want you to practice verbalizing, and you got to verbalize out loud, not in some weak little, no, I'm not sure kind of a voice, but, commit. All right, so one cycle is defined as the part of the waveform where it begins, and typically we look at where it begins from the 0 volts DC reference line, which is this dark horizontal line across the middle of your oscilloscope screen, where the waveform begins, and then it rotates, meaning it moves. It's rotating up to some positive peak, and then rotates back down over the side to some negative value, well, actually still positive, but it's decreasing down to 0. Once it hits the 0, that's not the end of one cycle. It then moves in a negative direction, and it moves in a negative direction below the 0 volts DC reference line to some negative peak. And then it rotates again and comes back up. It's still negative quantity underneath the 0 volts DC reference line, but it's decreasing in the amount of negativity until it actually hits the DC reference line right here. And that's where the waveforms will begin to repeat itself. So that is one cycle, my friends. So if we count, there's 5 divisions in one cycle. So you put down 5. Good job. Then you want to multiply that by the time base. Now, the time base is given in your Oscilloscopes display, and you have your time base written here. And the scale for this particular time base is 200 microseconds for each division. So you take 5 divisions, you're going to multiply by 200 microseconds for each division, you're going to get 1,000 microseconds. Well, if your calculator is working properly, and if you recall how to convert milli into micro, micro into nano, and so on and so forth, you should know that your 1,000 microseconds is the same as 1 millisecond. Remember, we always want to reduce the number of digits on this side and use the appropriate engineering prefix on this side. So that's 1 period is the time for 1 cycle. 1 millisecond, 1,000th of a second is how long it takes to go from the beginning of the cycle to the end. Now you need to calculate frequency, and frequency is calculated as the reciprocal of time. And so frequency is, when you punch it into your calculator, 1 kilohertz. All right, so that being said, what we're going to do is we're going to hit pause here and go to the calculator just to help refresh your understanding of how to use the calculator in your pursuit of comparing your understanding to the answers that we're showing on the screen. So I'm going to pause and switch to camera mode. All right, so let's go ahead and view our calculator functions. You should already have your answers written in your journal. So we're just going to confirm these with your calculator. So I have 2 calculators, a prefix calculator and then a non-prefix calculator. They're both excellent machines. I'm going to start with the prefix calculator, and we're going to start with 5 divisions, so 5, and we're going to multiply this by 200. And micro is keyed in as a shift micro, and it shows up as 5 times 200, and it shows you the little micro symbol. And all I have to do here is just hit equals, and it immediately gives us 1, and it shows us the engineering prefix of milli. So having the prefix calculator makes things easier for the beginning electronics engineering student. For those of you who don't happen to have this, I do have this recommendation. I have an affiliate link in the description of the YouTube. In a non-prefix calculator, if you already have one, no need to get another one unless you like the ease of using prefixes. The calculation is just as easy. It's 5 times 200. And what you do here, in order to key in the micro function, you use the 10x key, so 10x. You have to use change sign. Change sign is over here. It's the parentheses around the negative sign. Do not hit minus. Do not hit subtract. That does not give you a negative. You have to hit this, and then micro is 6. So now we have 5 times 200 times 10 negative 6. And how it appears over here is 5 times 200, and it just simply shows you micro. I'm going to hit equals, boom. And when I hit equals, it shows me 1 with a bunch of digits times 10 power negative 3. Well, 10 power negative 3 is milli. Now, we did show you on the display screen, we calculated 1,000 microseconds. And if you look at this, isn't 5 times 200 1,000? So 5 times 200 microseconds, isn't that 1,000 microseconds? How is 1,000 microseconds 1 millisecond? Well, I'll show you here. Let's clear, and let's do 1,000, and let's go to micro. So now I have 1,000 micro. 1,000 micro, if I hit equals, this will automatically convert, or I can hit engineering. I'm just going to hit equals, and this will automatically convert to the most succinct engineering notation and display of the value. And there you go, 1 milli. And the same thing is true over here. If I go to clear this and I go to 1,000, oops, 10,000, sorry, clear. Got a little carried away there. 10 power negative 6. So if I look at this, I've got 1,000 with the micro symbol here. I've got 1,000 micro, but at micro over here is shown as 10 power negative 6. The moment I hit equals, boom, it immediately does convert this to the most efficient display possible, 1 point, some number of digits, 10 power negative 3. This is 1 milli, and this is also 1 milli. So that takes care of your calculation for period. Now, in order to calculate your frequency, we said that frequency was a reciprocal of period, reciprocal of 1 millisecond. So on both of these, the reciprocal key is right here. It's a 10x negative 1, and here's an x negative 1, and here is an x negative 1. So if I hit reciprocal here, it's reciprocating the answer previously calculated, hit equals, and boom, this gives me 1 kilohertz. Same thing here. If I hit the reciprocal key, boom, we will reciprocate the previous answer calculated, which is what's on the display, hit equals, and there's my kilo over here. Kilo over here is shown as 10 power of 3, which is 1,000, so 1,000, and this is 1 kilo. So both of these represent kilo. One is showing you in engineering notation, one is showing you in the actual prefix. Okay, so we have just finished verifying in calculations our results demonstrated on the calculators themselves. Going back to the screen mode. Okay, so back on screen mode, yes, we verified these quantities via the calculator. Now let's go on to the next part of the yellow box calculations we need to do for this particular task, number 1. So the next sequence of considerations we're going to be looking at is this. I do make a recommendation if you don't recall how to use voltage divider formula, VDF is the abbreviation for voltage divider formula. If you don't recall how to apply voltage divider formula, don't have it written in your journals, then please do revisit my DC topic number 3 YouTube training lesson. And that covers your voltage divider formula very well, describes what it is, how to use it. I have reiterated the formula on the screen in the white box. The white box shows VRX equals, in parentheses, RX over R total, close parentheses, times the voltage source. What is RX? Well, RX is your resistor of interest, if you will. And so Rx could be represented by any particular number. So if we're interested in the voltage across resistor number 1, the 1 kilo ohm resistor, that is shown as the first resistor of the sequence of 3. If I'm interested in the voltage across that particular resistor, then in the formula, I would rewrite the formula as VR1 is equal to R1 over R total times the voltage source. Anyway, go back to the training video if you don't recall how to use it, or look at the formula and see if you can apply the formula in order to run the sequence of calculations. The first calculation, of course, is R total. You should be able to know how to calculate R total by now. We've been doing this for a number of lessons so far. And the one given that you are shown is that the voltage source is given as 1.5 volt peak. I repeat, 1.5 volt peak. So from there, you should be able to run with this and be able to do these calculations with confidence. There's a big red stop sign, so you know what that means. It means that we are going to put this on pause. You need to put this on pause and commit to pulling out that calculator and making your determination of what these values are. Commit your answers in writing into your journal. as the answer box shows, RT equals, you write down RT equals, and then you write down the value of RT. And the same thing true with these other calculations, write them down in your journal. And then we'll compare in a moment after the pause. So we're going to go into pause now. Well, welcome back, my friends. Yes, hopefully your answers calculated will compare with what it is we have on our screen. The R total is the sum of the three resistors that are in series. So 1,000 plus 5,100 plus 2,000 works out to be 8,100, which in proper engineering notation, we will write as 8.1 kilo ohms. The omega symbol is what's used to designate the quantity of ohms. So that's the first calculation you need to make. That's critical. Then we're going to use voltage divider formula and apply it. Now, if you don't get these answers, let's go ahead and review how this is done. I spoke the formula a moment before we went to the pause, but now I have it written down so that you can review this. Take a look at the example at the bottom. If you take a look at the example at the bottom of the screen, you will see I'm looking for a quantity called VR1 peak. So voltage across resistor number 1 in peak form, all right? So as I look at the formula in the white box, it says I'm going to start off with, in order for me to determine this voltage, I'm going to start off in parentheses, Rx over RT. Well, it makes sense, I hope, that if we're looking for the voltage across resistor number 1, we use 1K as the numerator and divide by 8.1K, which is our total, in the denominator. We close parentheses. That takes care of your fraction. That takes care of how this voltage is going to be divided across the first resistor. Then you multiply this by 1.5 volts, and hopefully you will get these quantities. So you want to compare these to what it is that you have. I'm not going to read them off to you. You can pause the video and double check these quantities. Now, if you don't have these quantities, write these answers down. And after you've taken a moment to copy them, I'm going to put this back on pause and I'm going to do the calculations with you. So we'll switch to camera mode in just a moment. Okay, my friends, in camera mode. So what it is we're going to look at is the very first calculation. And the first calculation in parentheses is 1 kilo over 8.1 kilo. Now, just as a point of interest, if kilo is in the numerator and kilo is in the denominator, we don't have to key in the quantity of kilo, meaning all I have to do is key in 1 divide by 8.1. I don't have to do 1 kilo divided by 8.1 kilo because the kilos cancel each other out. So it's simply 1 divided by 8.1. I could put this in parentheses or not, since this is an algebraic calculation. I can just multiply right now by 1.5, which is the voltage, and the display should show me immediately, hey, guess what? My previous screen, and you have written down a copy from my screen, 185.19 millivolts. There's your milli right there. Volt peak. Now, how do I end up with 9.19? In, I think, DC training number 2, we talked about how to round off your calculations. So look at DC training topic number 2 or topic number 3, how to round things off properly. But we will round to the 100th of a decimal place. So this 1.85, this 0.185 becomes 0.19 in our answer sheets. And this is just as easy to do on this calculator as well. So I'm simply going to take 1 divided by 8.1 times 1.5 equals. And interestingly, this one shows up in scientific notation. I can convert this into engineering notation very easily by touching the engineering button. And it'll change this 10 power negative 1, which is useless to us, to some multiple of 3. So 10 power negative 3, negative 6, negative 9. those are engineering prefixes or associated with engineering prefixes. And so your 10⁻³ is milli. And again, we would round this the same way, 185.19 millivolts peak. The same is true, and I'll do one more calculation, won't do them all. For the second resistor is 5.1. So 5.1 divided by 8.1 times 1.5, bam, there you go. You have 944.44 millivolts peak. And then if I clear, we'll do the last one here. This will be the last one's a 2K ohm. So 2 divided by 8.1 times 1.5 equals, bam, there you go, 370.37 millivolt peak. So that's how we do the calculations on these calculators. Let's go back and see how this compares with our screen. Switch out of camera mode, back into screen, and there we are. Yes, those answers we just calculated, we verified, and now we're ready to move on. Now, the next sequence is a bit more interesting. So this first thing that we needed to do, let's just recap. We needed to find the voltage across each resistor because we said that a string of resistors, a sequence of series resistors is nicknamed a string, like a string of pearls, and I have a string of 3 resistors. We needed to find out how much of the 1.5 volt peak source, how much from the signal generator, how much of it is going to be divided across R1, divided across R2, divided across R3. It would be good for us to reiterate at this moment some principles behind series circuits. First of all, the current is the same through all parts of the circuit. Secondly, there is a proportional distribution of voltages across the resistors. What this means is, in short, the largest ohmic value, right here, which is the big one, 5.1 kilo, will have the largest voltage drop, 944.44 millivolt peak. It does. Which one of these is the smallest ohmic value of the sequence of 3? The 1 kilo ohm resistor here, and that means it should have the smallest voltage drop, which it does. So there is something we call proportional distribution in a voltage divider, where the voltages are distributed in proportion, which is your formula. This formula of Rx over RT represents a proportion of how the string of 3 resistors actually divides the voltage. Again, that's review of some previous topics, but if you hadn't seen those or don't recall that concept, that principle of series circuits, it doesn't hurt for us to review it. All right, so the next slide, as I've said, is of particular interest because it relies on these values that we've just calculated. You have these now written in your journal. The next sequence is more practical. It talks about, let me go here, oops. Here we go. We are now interested in the specific voltages, what your voltmeter, what your oscilloscope will show us at the various points with respect to ground. That's the terminology that's used. So that means if I'm interested what happens at point A, I'm going to put the red probe at point A and the black probe goes to ground. So I'm measuring across 3 resistors. At point B, take a look at point B on the schematic. I would have the red probe at point B, the black probe would go to ground. I'm actually measuring voltage across 2 resistors. And then if I go to point C, red probe to point C, black probe to ground, then I'm only measuring the voltage across 1 resistor. Why this is significant, why this is helpful, this is called technician test point voltages, and that's discussed in a previous DC topic number 8. Review that. I won't get into details of that right now, but DC topic number 8 will explain fully the significance of technician test points. It allows you to very quickly test various points on a schematic or test various points on a circuit on the board and determine whether your circuit's working properly or not. So you need to be able to determine what these values are before you go sticking your probe into the circuit board and start measuring things. You got to have some idea what these values are going to be first and foremost. So we are looking for, as the description shows, says, remember, technician test point voltages from DC topic number 8 for determining voltage VA, voltage at point A, voltage at point B, and voltage at point C. Now, in quotes, with respect to ground is a very common phrase that's used in the world of electronics engineering. And so get used to seeing that. We'll talk more about that as we describe what happens in the next slide. So your task, determine the peak voltage at A, peak voltage at B, peak voltage at C. Once you have the peak voltages, then convert them to RMS. So RMS formula is given to you here. The voltage RMS is equal to 0.707 times voltage peak. Got that? Okay. All right. So why are we calculating peak and why are we calculating RMS? Well, my friends, the peak is going to be something you're going to see graphically on an oscilloscope. VRMS is the digital form of the AC that you're going to see on your digital voltmeter, your digital multimeters set to voltmeter mode. That's the value that will display on your DMM. So that's why you have to have both peak and RMS, or at least the understanding of how to calculate the peak and how to calculate the RMS. So the 6 calculations for you to do here, my friends. Look at the stop sign. Guess what? You are tasked with doing the calculations. Okay, so put this video on pause. And as you put this on pause, we will come back in a moment after you've done your calculations and have committed your answers into your journal. Again, legibly and in big letters, so big numbers, so you can see that you're tracking, or if there's a mistake, we'll be able to talk about how that came about. So put us on pause. Come back in a moment. All right. Let's see how you did. As you compare your calculations that you've written down in your journals, let's take a look at the voltage at point A. The voltage at point A is the source voltage. If you take a look at the schematic, the voltage at point A is at the top of the 3 resistors, and it is the signal that is directly out of your signal generator. So whatever's coming out of the positive terminal of your signal generator is also being read by the positive terminal of channel A, channel 1 of your oscilloscope. So we stated that the voltage source was 1.5 volt peak. Boom. Your voltage at point A is going to be 1.5 volt peak. No difference there. Then you convert the 1.5 volt peak into an equivalent RMS value. How? By multiplying by 0.707. So you should have these values calculated, written down. And if you don't have these values, these correct values calculated on your own journal, then don't erase anything that's in your journal. Just draw a diagonal line through your answer that may have been written in error, calculated in error, and write the correct answer next to your answer that you've written down that may have been incorrect. If it's correct, put a check mark and pat yourself on the back. At point B, we calculate 1.31 volt peak, and we measure 925.57 millivolts RMS. At point C, we calculate 370.37 millivolt peak, and RMS is 261.85 millivolts RMS. Double check these and see if they are what you have. What we'll do in just a moment is put this on pause to go to camera mode, and I'm going to do a couple of these calculations with you. Or actually, let me just switch right now off of screen mode into calculator mode, and in calculator mode, turn these beasties back on. And the first calculation was to take the 1.5 and multiply this by 0.707. And so 1.5 times 0.707, this is how we convert the peak into RMS format, and then hit equals, and it works out to be, as we would round off, 1.06 volts, and we would write the answer as V with a subscript RMS. Okay, the 1.5 started off as a V lowercase p, or V with a subscript P for volt peak. And in this answer, we would write as 1.06. Again, we round to 2 digits after the decimal point, VRMS. Now, clear? And the next voltage calculation at point B is actually the sum of the previously calculated values. That's the sum of the voltage across R2 and the voltage across R3. If you look at where point B is on the previous screen schematic, if you don't have it written down, hopefully you have it copied down, but point B sits on top of R2 and R3, okay? So just as a reminder, now let's just go back to here for just a moment. Take a look at point B. So point B sits right on top of R2 and right on top of R3. So that means the voltage at point B, and look at the phrase, with respect to ground, okay? So the voltage at point B with respect to ground means the red probe goes to point B, black probe goes to ground, which is point D. So we're measuring the voltage across 2 resistors. So what we ought to do in order to find this value, we want to add the previous value of voltage across R2 and the previous value of the voltage across R3. And what's that going to be? Well, you have this written down previously right here. So the voltage across R2 was the 944.44 millivolt peak. The voltage across R3 is the 370.37 millivolt peak. So let's switch to camera mode. And in my camera mode, what we're going to do is clear, and we're going to do 944.44, and milli is engaged here as a shift milli. So you can now see I've got 944.44 milli, and now I'm going to add that plus the 370.37. And again, this will be a milli right there. And then hit add or equals. And there's my 1.31 milli VRMS. Okay, so that will be, if we switch back out to the screen, go to share. So we add these two values of voltage, the 944.44, the 370.37, in order to calculate the voltage at point B with respect to ground. So our calculator just showed us 1.31 volts peak. And let's see what the answer sheet showed us. There's your 1.31 volt peak. And when you convert that to RMS, you multiply this value times 0.707, and you will get 925.57 millivolts RMS. The also true will be the voltage at point C with respect to ground. That is simply the voltage across the third resistor, which we previously calculated as 370.37 millivolt peak. So what we previously calculated as voltage across R3 also happens to be the same voltage at point C with respect to ground. So the red probe at C, black probe at ground is the same as the red probe up here above R3 and the black probe below R3. They're going to be the same value. So that in peak format, that'll be 370.37 millivolt peak. Your RMS, simply multiply the 370.37 millivolt peak times what? 0.707, and you calculate this value. Now, we will come back to this slide and these values time and time again as we move on through this lesson, because when we go to make these measurements with the digital multimeter, or make these measurements with the PicoScope and the FNIRSI Oscilloscope, we want to compare back to the screen these values when we're checking voltages. Okay, some more things to do coming up right here is this. Haha. You, again, need to calculate what's in the big yellow outline box, and that is the voltage source in RMS format. And then we're going to calculate the current in RMS format. Is there such a thing as peak current? Yes, there is. We just can't measure peak current. So current, as we've measured before, was with our digital multimeter. So your digital multimeter, when you measure AC, is set into the AC mode. And when you set it in the AC mode, your digital multimeter will not show you a peak quantity. It'll always show you a quantity in RMS. So that being said, if I want current, if I need to determine current, and the current needs to be in the form RMS format, I'm going to need to use Ohm's law. Ohm's law is reiterated for you on the right-hand side of the screen. If I'm looking for current and I circle the letter I, if I circle the letter I, that's what I'm looking for. That's the goal. You can, on your screen, put your thumb over the letter I. Physically, just put your thumb on the screen. What do you see that's left over between the quantities in the triangle? You have a V on top, you have an R on the bottom. So the formula from the triangle of Ohm's law is very easily determined. I for current is equal to voltage over resistance. Which voltage, which resistance? Well, if you're looking for total current, then you better be using total voltage divided by total resistance. So total voltage in RMS format was some quantity that you determined a moment ago. And then from there, you divide by the R total in order to calculate the current. So what's the direction say when you see the stop sign? You pause the video, you do the calculations, you write down those calculated values into your journal, and let's see how you do in a moment when you come back from your pause. Okay, you figure out everything already? Hopefully you've done so. Let's go ahead and take a look and see what the answers work out to be. There's only 2 calculations here, so hopefully you're spot on. If not, we'll do some explanation to help you out. No worries. All right, so here's the answers. We had previously calculated the voltage at point A, which is your voltage source, which is the same as voltage total, of converting the 1.5 volt peak into RMS. How did we do that? We used the formula in the middle of your screen. So we took the voltage peak of 1.5, we multiplied by 0.707, and we calculated 1.06 volts. And we have to write down the answer VRMS. If you mean peak voltage, you have to write down V with a P. If you mean RMS voltage, you have to write down the capital V with RMS. So this is in RMS format. And once you have the RMS voltage total, then you can divide by 8.1 kilo ohms, which is my RT. And lo and behold, you calculate 130.93 microamps RMS. Micro. What's that look like on your calculator? All right, let's take a moment and see what this looks like on your calculator. I'm going to go to camera mode. Okay, so in camera mode, we're going to clear. And so you took the 1.5, you multiply by 0.707. Was the zero necessary? No, but I just put it in there. So 1.5 times 0.707 will give me the RMS value, because that's a peak value. I want this RMS. So my RMS value we previously calculated, and I just double checked, is 1.06 volts. And we would write that as 1.06 with a capital V and a lowercase RMS, or subscript RMS. Now, this is your voltage total that you can read on a digital multimeter. We're going to divide this by the total ohms in order to determine the current. So we hit divide 8.1, and the kilo here is a shift. Kilo is on this calculator right there. So there's my 8.1 kilo, hit equals, and guess what? I calculate 130.93, and look at the symbol that it shows us up here. It's a micro. Micro what? Current is measured in units of amps. So my answer should be 130.93 microamps. How's it look on a non-prefix calculator? Same thing. Sequence 1.5, and we're going to multiply this by 0.707. And that's equal to the RMS voltage. And then we're now going to divide that by 8.1, and kilo is set up as the 10 power X key right here. and kilo is 10 power 3. So I'm just going to hit 3. So there it shows up as answer times 8.1 times 10 power 3, which is what I have here. Answer divide by 8.1 kilo, and there's my kilo over here. Now I'm going to hit equals, boom. And the calculator spits up some power of 10 that's not a multiple of 3. That's useless to us. We need to convert this to engineering notation. We have a handy engineering button right here. We tap it, and it'll immediately bring us to the most appropriate engineering prefix, the appropriate numeric display. So 130.93, 10 power negative 6, which is 130.93 microamps. So you want to feel comfortable with understanding 10 power negative 6 is in fact a micro, and you would write down the micro symbol on your answer sheet. You wouldn't write down 130.91 times 10 power negative 6. That's not how you write it. You write it using the engineering prefix. Okay, so that being said, let us now go back to the screen mode. Okay, so in screen mode, yes, there's your answer. And now we can move on to the next step. So the next step is for us to look at oscilloscope measurements. Okay, again, I've reiterated the two screens. The one on the upper left is the PicoScope screen, and the one on the lower right is a photograph of the FNIRSI screen. The circuitry is shown in the lower left inset, 3 resistors in series, and I've got points A, B, and C, and D labeled with little stickers, and then the schematic with points A, B, C, and D is also shown in the middle of your screen. So for us to do this, before we do the oscilloscope measurements, there's something that's very important for you to understand, and that is this point here, the concept of loading. Loading. All right. Circuit loading effects on your measurements. We had in a previous DC topic number 9 lesson, I had compared, we together have compared loaded circuits versus unloaded circuits. So unloaded versus a loaded voltage divider. If you don't recall those terms or haven't seen them, or you've seen the video but didn't write the information down in your journal, and take a moment and go back and review loaded versus unloaded voltage dividers. A very important consideration, because we're going to see this when we hook up our oscilloscopes to our circuitry. So in the second paragraph, the loading of added devices definitely changes the original circuit parameters. Okay, we just can't tack on something to the signal source and expect everything to remain unaffected. And so a load, if you will, is anything that has current flowing through it. So your resistor is a load, your switches are a load, your potentiometer that we've played with previously is a load, your air conditioner is a load on your electrical system, your refrigerator is a load. If it has electricity flowing through it, then it's called a load on the electrical circuit. So your breadboard circuitry, the circuitry that you built on the breadboard, the simple sequence that we've built for 3 resistors, may have a loading effect on your signal generator. Some more than others. It just depends on your signal generator. So it may have something called a loading effect on your signal generator, such that the required V out from your signal generator may appear lower when you measure it off the board. Okay? So what that means is, if we require a 2-volt peak from our signal generator, when we hook it up to the circuit on the board, what we measure on the board may not be 2-volt peak. There may be a loading effect of the circuitry on the board as current flows through it. It may be drawing more current than the output of your signal generator is designed to sustain. And so we may see a slight difference. So let's see how this loading effect works graphically on an oscilloscope. Here we go. So in this particular case, I found it easier just for a moment to demonstrate initially on the PicoScope display some things of concern. So the topic at the top shows unloaded PicoScope measurements. So unloaded means if you take a look at my schematic, I've got the three resistors, I've got the wire going to the blue rail, which is my ground. But if you take a look at the top, I don't have any connection right now between the red rail and the first resistor. There is nothing there. This jumper wire, the orange jumper wire, previously connected the red rail to the first resistor, but I've removed it. So what it means is my voltage source, which is on the red and blue rails, has no load of three resistors attached to it. So this is what we call unloaded. So when it's unloaded, my signal generator is connected to the red rail, and my oscilloscope is also connected to the red rail. So with the signal generator putting in 2-volt peak and the oscilloscope connected to the same connection point, it should show 2 volts peak. So take a look on the display here. The signal generator parameters are specified 1 kilohertz at 2-volt peak. What is actually measured on the waveform? On the waveform, I'm using these dashed horizontal lines in a tool we call cursors. So it's like a ruler, and I place them. I can move this dash line up or down, and I want to move it all the way up to the tippy top of the sine wave, and it shows I've got 1.952 volt peak. Is that pretty close to 2-volt peak? Pretty darn close. Slight difference there. Why is there a slight difference? Well, even with the circuit unloaded, as you can see, that orange jumper is removed, even with the circuit unloaded, I still have the metal bar underneath these rails. I still have the leads themselves. I still have the little jumpers with the alligators connecting the leads to the rails. So there may be some slight loss due to the slight amount of resistances at the interfaces that we encounter with our hookups. So yeah, it's going to be close, but it's not exact. What happens when we load the circuit, meaning when I actually connect the orange jumper wire back in, you'll see something pretty dramatic happen. So we want to look at two places. The signal generator is a 2-volt peak, which is a 4-volt peak to peak, meaning so here's 0 volts reference line, and you count 4 divisions up to the peak. So 4 times my 2-volt per division. So right here's my channel A parameter. My channel A parameter is 2 volts per division. Channel B is off. I only need one channel at this point, so I only have one trace. So at 2 volts per division, how many divisions from the 0 line to the top? 4 divisions. And so, oops, what do I have here? Oh, take it back. I have switched some things around. In any case, if I go to hook this up, I have 1.952 is what the dotted line shows. The ruler shows 1.952. If I double that, shows my peak to peak at 3.947, and that's pretty darn close to a 4-volt peak to peak. Very little loading based on the circuitry so far of the power rails, the jumper wires, and the connections. Now, watch what happens when I actually load the circuit, meaning I'm going to put this orange jumper back in, and then this circuit of 3 resistors will now be attached to the power rails. Look what happens with these values that are measured. Boom. Look at that. Wow. So what we have is we haven't changed the signal generator. Signal generator is still kicking out a 2-volt peak. But I have the orange jumper in place. The orange jumper is taking current from the red rail to the first resistor, making a connection from the red rail to the resistor. Follow these resistors down to this blue jumper and brown jumper to the negative rail. So I now have a completed circuit. Electricity is now flowing from the power rails through the sequence of 3 resistors. By having this sequence of 3 resistors loading onto the power rails, my voltage now at the peak sags a little bit. Instead of the 1.9 something volt peak that I had previously, I now have a 1.78. It has dropped a little. and that's called loading. Okay, so the loading is a physical connection, and the loading effect is that this physical connection of these resistors does draw current, and as it draws current, if the power supply of the signal generator is not high current enough to be able to keep things stable, then we're going to see a little sagging. We're going to see what's called a loading effect. How much did it change? It changed from 1.95 in a fraction to 1.78. So it's showing here in the red box in the dashed line. It's showing here in the ruler value, and it's also showing as a peak to peak of double this quantity to be 3.657. So if we read the narration, signal generator output of 2-volt peak works out to be 4-volt peak to peak, but the loading of the circuitry reduces the desired voltage source on the board. Instead of 2-volt peak on the board, it is now on the board at 1.78-volt peak, or this amount of voltage peak to peak. You say, well, maybe something was wrong with my setup. Maybe the 2-volt peak was a little too out of bounds for whatever reason. I'm going to change the voltage value from 2-volt peak to 1.5. See if that gives us any change. So I now have the voltage from the generator, still 1 kilohertz, but instead of 2-volt peak, I have it at 1.5-volt peak. This is unloaded, as the title of the slide goes to show, and you can see my orange jumper removed. Okay, so the orange jumper is removed. There is no connection of these 3 resistors to the power rail except through the bottom, but we need both top and bottom connected in order for electricity to flow. So this circuit is an unloaded PicoScope measurement. So while it is unloaded, take a look at my signal out. My signal out is 1.5-volt peak. What is my signal being read by the oscope? It's 1.474. Again, not quite the same. It's tiny bit less, just a tiny bit. Why? Because there's some resistances that we're going to see at the interfaces of these connections, some resistances of the jumpers, some resistances of the jumper rail itself. But again, pretty darn close to 1.5. When we go to load the circuit, you'll see this come down quite a bit. So the board measurement of the voltage source and channel A on the red rail, both VS, from my signal generators on the red rail. Channel A of the oscope is also on the red rail right here. They're both connected together onto the red rail. Shows an unloaded voltage source at 1.474 on a 1.5-volt peak signal output. Now, what happens if I load the circuit? If I load the circuit, here, that means if you look at the circuitry, I've now reconnected the orange jumper wire. I now have continuity, and the electricity is now flowing through the 3 resistors. My signal generator hasn't changed. It's still 1.5-volt peak. However, my voltage on the board has changed quite a bit. My peak voltage on the board has dropped from the 1.4 and a fraction now to 1.3 and a fraction. That's quite a bit less. And so it shows up as 1.349 here. On the ruler box, it shows up as 1.349. And instead of a nice 3-volt peak to peak, which is what I have coming out of the voltage generator, it is 2.734 volts peak to peak. Here's my numbers compared and contrasted in white down at the bottom of the slide. Okay, so this is what happens on the PicoScope. Let's see what happens on the FNIRSI oscope. Right. Oh, actually, before we get to the FNIR oscope, I decided, since I happen to have one, I'll go to my Rigol benchtop oscope. And so the benchtop oscope will show unloaded versus loaded. And let's see what happens here with the benchtop oscope and benchtop signal generator. So I'm using a Rigol DG1022 signal generator. I can have that. I do have that set at 3-volt peak to peak, which is 1-volt peak, 1.5-volt peak. This is unloaded, as the circuitry on the board shows. There's no jumper wire between the red rail and the first resistor. So while this is unloaded, I have 1.5 volt peak coming out of this function generator, and this is reading on the oscilloscope 1.520. Okay, slightly higher. And you may find some of these variances that will occur between your signal generator and what the oscilloscope actually reads. There may be some tiny, tiny fraction of a difference. So on my signal generator, it says 1.5 volt peak, which is 3 volt peak to peak, and the oscilloscope actually measures something slightly higher. So we get a bonus of 0.02 volts peak, 2/100th of a volt extra. Never bad when you have extra. Bonus is always good. So the board measurement is of the source, and the board measurements channel A of the oscilloscope. Both of these are attached to the red power rail, and it shows I have an unloaded circuit voltage source on the board of 1.520 volt peak against a 1.5 volt peak signal generator output. Now, we're going to load this and see what happens next. Okay, so loading, this is now a loaded circuit, and as you can see in the schematic on the circuitry on the far left, I've got that orange jumper wire in. I do have continuity between the red rail and the first resistor, all the way through the string of resistors down to point D, and then into the brown jumper wire into the blue rail. So there's a complete path for current to flow. We call that, starts with the letter C. What do we call a complete path for electricity to flow? This is a test question. Come on, it's in your journal. You should remember. And again, if you can't recite some basic answers to some basic questions, you need to practice speaking. Okay? It's like trying to learn a foreign language. You cannot learn a foreign language just by reading a book. You cannot learn a foreign language just by listening to MP3s. You need to speak that language in order to become confident and competent in pronouncing words properly and confidently. So the same thing is true in electronics, engineering, electronics technology. You need to speak the vocabulary. And so we call this signal generator output of 1.5 volt peak. We call this connection, this complete connection of wiring to the power rails. We call this continuity. That's the word we're looking for, continuity. Continuity means a complete path for electricity to flow. So without that jumper, we do not have continuity. With the jumper wire, we have continuity. Good review of a very important vocabulary word. Anyway, so let's take a look at this. So while this is unloaded, we had a 1.52 volt peak. We had a little bonus of 0.02 volt peak. Once we loaded this, guess what? This measurement is right off the board. My channel, what they call this one, 2 and 3. So I have channel 2 and I have channel 3 connected, and the channel is showing us a value on cursor A of 1.470. Ooh, what happened to my 1.5? It sagged a little bit, okay? My signal generator is still kicking out a steady 1.5 volt peak, which is a 3 volt peak to peak, but my oscilloscope measurement on the board has dropped a little bit. What is that? That is called the loading effect of the circuitry onto the oscilloscope readings. Now, let's see what we can do about this. Let's see if we're going to do this in the next slide or not. Aha, compensation. There we go. It is my next slide. So we can compensate, my friends. We can fix this. This is an easy fix. And you'll find this time and time again with your benchtop machines at school and also other signal generators connected to other oscilloscopes. We can compensate if there is any kind of loading effect. What that means is if you look at the circuitry that's on the left, I have continuity. The orange jumper wire is in place. I have the circuit of 3 resistors loading my power rails. And what I can do is on my signal generator, bump it up a little bit. So I'm nudging it up instead of the 1.5. On my signal generator, I'm nudging it up to 1.61 volts peak, a little higher here in order to achieve what on my scope, as well as my board. Take a look at my cursor A. My cursor A shows 1.50 volts peak. All right. Cursor A is the solid white line that's sitting on the top of the big waveform, and that's 1.5 volt peak. Now, that being said, cursor B is showing me 910 millivolts peak, which is my output at point C. So I have dual trace. And I have a question for you. It's another test question. It goes back to the previous training video, AC topic number 1. Here's the question, and perhaps you should write down the question at this point. What is the phase relationship of these two waveforms? I repeat, what is the phase relationship of these two waveforms? So as you write that down, think about it. If you can't answer this question, then you need to review AC topic number 1 video. But in short, if you did answer this correctly, you would have said what? These two waveforms, the dark blue one and the light blue one, what is their phase relationship? They are said to be in phase. In phase, what that means is both peak positive at the same time, both peak negative at the same time, both cross over 0 at the same time. When all of those parameters are spoken in that way, then we can say that these two waveforms are in phase. Didn't know you were going to get quizzed along the way. This is what we're going to do a lot of, my friends, is that this is intended as a practical, hands-on, thought-provoking training video, and you will be asked from time to time, again, things that you need to remember from previous trainings in order to be confident and competent moving into future training videos. All right. So this is the way I've structured these training videos. And if you like this approach, then please by all means give us a thumbs up. Hit subscribe. That helps the YouTube metrics and allows me to be supported to at least with pat on the backs anyway, so that I can continue making more of these training videos. All right, so this is called compensating. So we're compensating the loaded bench scope measurements by bumping my signal generator up just a tiny bit in order to achieve the desired volts peak that are on the oscilloscope. Now, can I do this also with my PicoScope? Yes, my PicoScope had some sagging previously, so meaning that when I had the circuitry loaded, my PicoScope showed something less than the 1.5 volt peak measured by the oscilloscope on the board. So take a look here how we're compensating. I want 1.5 volt peak right here at the top of these peaks on the board, on the red rail. And how do I achieve this when this circuit of 3 resistors will load my signal generator? What I'm going to do is I'm going to bump up the signal generator. So the signal generator is going to be bumped up just a touch. So instead of 1.5, I have to bump it up a little bit, as I did on the benchtop signal generator. This is now bumped to 1.67 volt peak. And when I bump up my signal generator, then my signal on the board will be a nice solid 1.502. That's pretty darn close to 1.5. 1.502, that's 2,000th of a volt difference. You try to get that. Takes a little bit of patience. All right, so as we look at this, the ruler shows for the blue waveform 1.5 volt peak, shows for the red waveform 373.3 millivolts peak. So the red waveform, as you can see with this probe at point C, is measuring the voltage at point C. Now, you can compare these with your previous calculations of the voltage at point C. You've done this a couple of slides back. You have the answer written in your journal. Is the voltage at point C that we calculated something close to 3 73.2 millivolts. Hopefully so. Okay, hopefully so. All right. So now that being said, yes, the bottom says we compensate by setting signal generator out to 1.67 volt peak in order to achieve a voltage source on the board to be equal to 1.520 volt peak, and then channel 2, which is at point C, there's my channel 2 probe at point C, will show us 377.5 millivolt peak. Is this close to your calculations? Well, let's go ahead and review our calculations. Bam, look at that. We calculated 370.37. We measured 372 millivolts. Pretty darn good, okay? So as I said, we'll be coming back to this particular slide from time to time and see how we compare. Okay, moving onward. Let's take a look at our next slide. All right, let's go ahead and talk about what you're going to expect to see on your FNIRSI tablet, Oscope. And this is shown next to our recommended digital multimeter. Both the Amazon affiliate links for both of these are in the description below. What I've made recommendations here, actually, before I talk about recommendations, let's go ahead and talk about some of the specifications you're going to be realizing on this particular Oscope. The screen is 4.3-inch diagonal touch screen. I repeat, this is a touch screen. You notice around the perimeter of this particular device, absence of hard buttons. In fact, the only hard button on this is the power button, which is on the upper left-hand side of the machine. Otherwise, all the functions are adjusted by touch screen. So as this is a touch screen, I recommend using cell phone pens. You know, these pens, these are the ones with a little soft rubber tip, little sponge rubber tip that you use on your cell phone screens. They're very, very smooth, very soft. They will not scratch the surface of the screen, but they give you more precise point and control than your fingertip, especially big hammy fingers that I have. I have no hope of being able to do some fine adjustments on a touch screen. So I highly recommend cell phone pens for your touch screen. So this is set up with BNCs. We talked about what BNC connectors are. So 2 BNCs for channel 1 and channel 2. So these are full-size connectors, full-size BNC connectors. And then there is a third micro BNC connector. So this is unique to this particular machine. Some devices will have a third BNC right here. We'll talk about that later, but this one has a micro BNC. BNC is a bayonet connector. So this has a USB-C charging port on the side, and it's called the tablet Oscope because it's like a tablet. As we go to take a look at other characteristics, once you turn the machine on, what you're going to do is you're going to touch the menu button with your cell phone pens. When you tap this, it'll call up wherever it was before. It'll call up this particular screen of which you can slide left, slide right. So whatever comes up, you're going to slide left, slide right, or swipe left, swipe right until you see the signal generator, signal source come up in the middle of your screen. Once you see signal source, then you touch, meaning you tap this. Once you tap this, then the control part of the signal source comes up, and you're going to set the signal generator to 1.5 volt peak, which is 3 volt peak to peak here. You can do this by clicking in here and typing in the number, or you can adjust this by moving the slider left and right on the touch screen with your cell phone pen. So you want to set the signal generator to 1.5 volt peak, which is 3 volt peak to peak, and you want to set your frequency to 1 kilohertz, which were the parameters that we had for the PicoScope, and the same parameters that we will have on our breadboard. All right, so next, swipe the touch screen sideways, go back to menus, go back to menu, and then swipe the screen left and right until you see Oscope. Once you see Oscope, you tap the Oscope logo, and then you touch the function button. Right down here is your function button. Then you will see a function screen, and on the function screen, you want to first tap, you're going to tap, will be the cursor. Now you can set cursors with vertical lines, X1 to X2 are your vertical cursors, or Y1 to Y2 are your horizontal cursors. We'll get into a detailed lesson on how to use cursors in a more specific fashion in a subsequent video, but the lines are very handy as rulers, if you will, that go to the top of the peaks of these waveforms. That gives us a reading what the V peak is visually. It's something that's very handy for us to be able to see. And the 4.3-inch screen is a really nice size screen to be able to see this. And as long as you're using a cell phone pen, yes, you'll be able to manipulate the movement of the waveforms up and down on the screen, and then the positioning of the waveforms relative to each other, and then also the positioning of the cursor. So all of this, like I say, you definitely don't want to do with your chubby fingers like what I have. You want to be using a cell phone pen. Now, that being said, after you have set the cursors, then you want to set your measuring parameters. Your measuring parameters, you touch this button on the function. After you hit function, you touch measure, and then you tap this upper left button for channel 1, you tap it again for channel 2. So you tap this back and forth until you see channel 1, and you select whatever parameters you would like to see on the display of your Oscilloscope screen. And then the same is true for channel 2. And once you've set those parameters, and what I've got is the dark buttons are unselected and the light colored ones are the ones I have selected. And the ones that I have selected will appear on my display screen at the bottom of my display screen coming up. And that should look something like this. There you go. So at the bottom, my display screen shows this information, and this is, again, a photograph of my screen. The FNIRS, this particular model, the 2C53P, has a USB-C port for charging, and the USB-C port is also there for connecting a USB thumb drive. And from the thumb drive, you should be able to output a diagram of this to your computer to go onto a larger monitor screen for review. I have not been successful with that I don't know why. I've tried a number of different thumb drives into the USB-C port. I've tried the thumb drive directly into the laptop. I just cannot get any signal out. I can save signals. I can save the signal all day long. It has a built-in memory, and I can save waveforms and recall them on the screen. But I have not been able to be successful in how to get this display onto the computer screen, other than the photograph that I've taken. So if you have any suggestions there, I think I've exhausted everything. Like I say, I've used a variety of different USB thumb drives. I've used USB flash drive, and the 2 gigabyte, 2 terabyte outboard drives, and have not been able to get anything out of that USB port. Anyway, that's why you're looking at a photograph, my friends. And the photograph doesn't capture the color, the vibrancy, and the resolution as effectively because there's some reflection. And I've tried to set up my camera in such a way that I reduce as much of the reflection as possible. But that's why you're seeing the display not as pretty as I'm looking with my eyeballs. But the important information is there. I can put the cursor at the top of one screen, one waveform, the second cursor at the top of the other one, and then the values, rather than squint and read this, I just have the values interpreted on the left-hand side, right-hand side of our display. So the channel 1 is showing us a volt peak that's pretty close to 1.5. It's slightly more. That has to do with a variety of circumstances why it's slightly more, as it was with my bench top. It was also slightly higher on my bench top. It's okay, as long as it's reasonably close. Channel 1 in RMS value is 1.1 volts RMS. Channel 2 V peak is 390. We calculated 370 and change, so not too far off. And then the RMS, we don't have to convert because RMS is one of those values that is selectable in your menu. You can see I've got an RMS value right here of channel 2 of 281.25 milli VRMS, and I've got my channel 2 peak output at 390.62 millivolts. So these values, I don't have to try to read off of my cursor. This comes up automatically as I've selected these parameters from my setup to be put on the display screen. Pretty handy. The V1 RMS is shown here. 1.10 is what it rounds off to be. My peak to peak at 3.1 right here, peak to peak at 3.1. Ideally, it would have been 3.0, but again, we won't sweat the tiny fraction of a difference. Again, we're dealing with imperfect Oscilloscope probe leads, imperfect situations that are happening on the breadboard, a number of things. As long as we're close, we're happy campers. And the frequency, it's given right here. This is automatically reads this out to you as 1 kilohertz. You don't have to be here counting the number of divisions left to right for one cycle in order to determine period, in order to reciprocate it, in order to determine frequency. Frequency is automatically displayed as one of the parameters we selected from our setup. Then there's something called duty cycle. I hadn't talked about duty cycle before, but since this happens to show us duty cycle, a 49%, what duty cycle is the percentage of the positive waveform in comparison to the entire waveform. And for the most part, the duty cycle should be 50% or something pretty darn close to 50%. What that means is the positive half cycle of this wave is equal in time to the negative half cycle of the display, okay? We will find duty cycle to be a more significant topic of discussion when we get into square waves, but that's reserved for a later video. But since it happens to be part of the display right here, duty, so I figured, okay, I'll just make note of it and introduce you to the term now. Okay, I've come back to this slide because I said that we want to come back to this slide a number of times as we compare these numbers to measurements that we're about to do. And as we take a look at these values, you should have them recorded, the voltages at specific points with respect to ground. The current you should have recorded in terms of milliamps or microamps RMS. And have these handy, because as we go through measurements, we will be looking to compare how closely our measurements are with respect to our calculations. So without further ado, we will continue to the measurements. Okay, I've switched to camera mode, and in camera mode, I wanted to compare you to be able to see the comparison between the PicoScope, the FNIRSI tablet oscope in comparison to the digital multimeter that we've been using for quite some time. The multimeters you can see set up this way, that size, everything is a happy camper. This is wonderful. The PicoScope is set up with 3 BNC connectors, bayonet connectors, if you will, channel A input, channel B input, and then my signal generator out. How they compare on the tablet scope, here's my BNC for channel A, BNC for channel B, and a micro BNC connector for the signal output. So they are functionally the same. So channel A, channel A, channel B, signal generator out, signal generator out. The on and off control of the tablet is shown here. Just one button to turn it on. Has a kickstand so that you can prop it up. The USB-C connector is right here for charging. And that's really all there is to the, oh, wait, no, take it back. There's more. Yes, This also has the bonus of a digital multimeter built in. So it has the connection ports for your BNC connectors. Sorry, I come back. Banana connectors has the banana connector ports like you do on your multimeter to these multimeter ports here. So there is a shows up as a 10 amp, milliamp, common, and then also this is your red connector. So these pull out of here and connect over to here, and life is good. So that's what's on this side of your tablet scope, the power button on this side of your tablet scope, the BNC channel indicators, and nothing on the bottom. Your Pico, if you look at this, your Pico is very, very thin by comparison. It's like half the thickness of this guy, and there is no on-off button. There's nothing on here other than a USB power connection. So it is receiving power through a USB connection, USB-B connector instead of a USB-A connector. Looks like a little house. And it connects here for power, and it also ports the information from this port to your laptop. The FNIRSI, this is a really solidly built device. It really feels substantial, really, really high quality, well built. It's got little rubber nubs on the four corners for shock protection, and it also keeps this from sliding around on your desktop. The Pico is also extremely well built. What was interesting is you don't see too many products manufactured in the UK. So this is actually manufactured in the UK, which is kind of refreshing since so many things come out of the Far East. Not to denigrate anything manufactured in the Far East at all, but it's nice to see something different. And this happens to be manufactured in the UK. All right, so we've compared the sizes. Now let's go ahead and turn this guy off, get rid of this guy, move this out of the way, and now see how we're going to hook things up. So the connections to the PicoScope are here. I have these connectors set here. So I'm going to do a connection of this BNC connector to channel A. The way these work is there are pins on here. There are pins, right? There's a pin, and they have to line up with the slots. I've shown you this in the previous training video, AC topic number 1. They have to line up with the slots, and you push in, and as you push in, then you rotate, and then it'll click solidly like so. And then this is my signal generator out. I'm going to use this. That's the connections here, and then this guy will power it up right there. Okay, so now this guy is powered up and ready to go. And the connections for this guy are also just as easy. Let's see where I set those. I believe I set those here. And let me make sure which one is which. I didn't color tag these yet. Okay, this will be channel B. All right. So take this one, we'll go into here. Again, line up the pins. You can see the pins, those little shiny tabs that are on either side, 180 degrees apart on the BNCs. Have to line them up with the slots that are in the BNC connector. So line them up and push down. And as I'm pushing down, give this a firm push and a twist. Rotates and clicks. And the same thing is true here. And give this a twist. Okay. All right. So let's go ahead and start with the FNIRSI and turn this beastie on. And sorry for the glare. Unavoidable. Sorry. We'll do the best we can. Press and hold. There's your diagnostic screen coming on, making sure everything is wonderful. And very nice. There is a menu button right here. Let me bring this down so you can see this a little better. Glare and all right, sorry. Can't help the glare. I'll do my best. There's a menu button right here. I'm going to tap menu, and then I can slide this left, right. So I have a signal source, slide this, there's my settings, slide this, my multimeter, slide this, my, slide it again. Oscilloscope. All right, so as I slide left and right with my cell phone pen, you can do this with your finger also. This particular part is pretty straightforward because these are large. So I'm going to go to, oops, that's your digital multimeter, by the way. Let's go back to menu and signal source. Now, once I get to signal source, touch it. Hello, there, okay. And this gives me my signal source controls. And my signal source controls allows me to select any of a number of like 12 different waveforms, sine wave here, square wave here, sawtooth triangle, half wave. Okay, we want sine wave, so we select sine wave. The frequency is displayed here. So if I wanted 2,500, 2500, so that's now 2.5. Can't read the number, I apologize. It's really hard with this amount of glare in the room. I apologize. Oh, there you go. Hold it this way. All right, if I wanted 2.5K, so 2500, now that's 25,000. Or if I wanted 1K, so 10, hit clear. And 1000, there's my 1K right there. Okay. All right. 3-volt peak to peak, which is a 1.5 volt peak. I can use the slider to change the value right here to anything in between, from some really, really tiny 1/10 of a volt value all the way up to a full 3-volt peak. Now, at some point in time, the slider will respond as well as it can, or you can just clear it and just punch in a number. So 3, 0. Okay, now I've got 3-volt peak. Again, that's hard to see, I'm sorry. A duty cycle, keep it at 50%. So sine wave, 1 kilohertz, touch something accidentally. So I want sine wave, 1 kilohertz. Oh, my voltage changed because my pen came close to it. All right, so I want a 3-volt peak to peak, which is 1.5 volt peak, 50% duty cycle. My signal source is now set. Okay, hit menu. And then from menu, I'm now going to go over to Oscilloscope. Oscilloscope function, I'm going to touch Oscilloscope. And once I touch Oscilloscope, can hit auto if my signal generator does need to be on. So I'm using a slightly different signal generator. Hold on. All right, I'm going to use the designated BNC, micro BNC connector. That's this guy right here, to the signal output of the function generator portion of the tablet. Take this and be very careful with this, because this it's going to be hard to replace if you damage this particular cable. It's not a standard BNC like the rest of these. Would have been nice if this was a standard BNC, but it isn't. It's okay. We will just be very careful. Take this and carefully plug it in. Push straight down until it clicks. All right, once it clicks, you want to reiterate your read the waveform right away, which is great. All right, so it allows us to be able to read channel 1 and also channel 2 information. The channel 1 information is my signal source, and that is coming in through here. And I'm going to need this in order to adjust my waveforms. So it goes to show channel 1, and I can tell which one is which channel 1 versus channel 2. If it's hard to see on your screen, but right here is designated channel 1, and if it's the same color as this waveform, it's a light blue. So I tap this in my channel 1 information goes away. If I touch this one here, this is a little darker blue, and that's happens to be for this lower trace is slightly darker. And if I wanted to set up its parameters, I could just tap this, and then I can call up its parameters and be able to touch what it is that I want to see. So if I wanted to go to do this, let me just go here for a moment. If I wanted to see these two in comparison with each other, or just read the information right off the screen, it's telling me I've got 1 kilohertz. It's telling me my duty cycle is 49%, which is about pretty close to 50%. Telling me that my maximum is coming in at 1.5. Let me move this over. 1.53 in order to read this value. 1.53 is pretty close to my 1.50. My RMS comes in at 1.12, which is pretty close to my 1.05 calculated, and a previous measurement of 1.1. My secondary is coming in at, let's take a look at where this other probe is connected. I've got this guy going to here, going to here, going to here, and let me double check. And give me a moment. Mouse. Need a surface for my mouse. I need a surface for my mouse. There's very little desktop left in desktop space here. Okay, it took a while, but I found an angle that at least allows us to approximate reading some of these, the information that's on the scope screen. It really does have quite a bit of information down here in the details. It tells us frequency 1 kilo, duty cycle 49%. It tells us right over here Vmax at 1.53, my VRMS for channel 1. All my channel 1 information is this light blue, and it's all of this light colored information down here. The darker blue information, the darker blue waveform, I have two pieces of information here, which are its V peak and its VRMS. So let's go to the light blue values. The light blue value does show us a Vmax, a peak at about 1.53. Now, that trace comes down right in front of the number. So I'm going to just touch this and move the waveform over, and voila, you can see this a little more clearly. And it does show up as a 1.53 volt peak, and then the RMS is calculated as 1.12 VRMS for the input channel. The output channel shows a Vmax of 387.50 millivolts, which is pretty close to our calculated value of 377. And then it does show an RMS. Now the RMS, again, the waveform comes right down in front of that. So I can take my touch pen and move this over like so. And then now I can read the value a little more clearly. And it works out to be 275 millivolts RMS, which is not far away from our 261 0.85 millivolts RMS that you should have written down in your journals. So let's compare and see how these values compare with your journal. Your journal peak voltage at point C was calculated as 370.37. Here it shows as 387.5. Again, pretty darn close, considering we have maybe a little more output, a little more juice coming out of here. And we do. Our Vmax peak, instead of 1.50, works out to be 1.53. So it's a little more juice coming out of the signal generator, even though the signal generator is set at 3 volt peak to peak, 1.5 volt peak. Even though it's set to 1.5 volt peak, it's going to be just a little hotter on the actual circuitry on the board. So these traces are reading information right off the board. And these wave shapes look to be in phase, and the wave shapes look pretty similar in size. And you know that that's not going to be the case, because your channel 2 is coming off of point C in your schematic. And point C in your schematic is one of the lowest values, should be 370 millivolts. But why is this 370 millivolt looks taller than the 1.5 3-volt peak of the input waveform. Well, they're on two different scales. I happen to have the channel 1 on a 1-volt scale, and I happen to have channel 2 on 200 millivolts. So if I were to change them to be the same scale, I'll touch channel 2, and then I can adjust the scale here. So let's make this 0.5 volt. Let's make this 1 volt. So both of these are now at 1 volt. So at 1 volt, both of these are now set at 1 volt per division. What happens is you can see this waveform on point C is quite a bit smaller in size than the input waveform. So the input waveform at 1.5 plus volts peak, and oops, come back here, and then the waveform at point C, quite a bit less. So we can see dual trace information on here very nicely. We can see if they are in phase or not simply by shifting the position of the waveform. Let me go ahead and move the position of the waveform. Let's go ahead and slide this one down so that it's at the 0 volts reference line. Touch this, come back here, touch this waveform. And here's where it gets a little tricky. Oops, come back here. Get a few more cycles on display. And let's see if I can control. Let's make this a little bigger so I can grab a hold of it. Okay, so now it's a little bigger, and I'm going to move it up so that it is right there. And yes, you can see they're both peaking at the same time. They're both crossing over 0 at the same time. I don't have them both quite at the 0 mark, but with some finagling, and you don't want to see me sitting here using the rubber tip pen to try to line these guys up with the 0 volts reference line, but close enough that you can see, yes, they are what we call in phase, meaning they both peak positive at the same time, they both peak negative at the same time, they both cross over 0 volt DC reference line at the same time. So they are in phase. They look, in fact, if you look at the dark blue trace, why is it bigger? Why is it taller than my input waveform? That's impossible. My input waveform is 1.53 volt peak, and my output waveform at point C is 387.5 millivolt peak. How's that displayed larger? Because of the scale. I have the channel 2 scale at 200 millivolts. We'll go here. If I change this back to the 1 volt per division so that it is same scale as the input, you can see, yes, the dark blue waveform is quite a bit smaller. Okay, so this is what the scope looks like. This is really well built, and I apologize. The zoom camera that I'm using, what I have to use for zoom, is not resolving this quite the way that I'd like to, but it's actually a much prettier display. And if you want to get a sense as to what the display actually looks like, the photographs that I've taken of this in the slide set, it shows a lot more resolution and much better colors than this is showing us presently on this camera system. So that is this guy. And then if I wanted to switch from here to the digital multimeter, I go switch multimeter, and then I would have to hook up the leads on the side and be able to measure current for you. And we can do that very easily. Let me go ahead and put this back on pause for just a moment. Okay, much easier to show you a photograph of the current measurement. So the slide goes to show how the current measurements compare between the tablet oscope by FNIRSI. I'll call it FNIRSI for the lack of knowing a better way of pronouncing that, in comparison to the digital multimeter we've been using all along in our lessons. So if you look at the probes as they touch into the circuit on the left, I created an open between the last resistor and ground, and the probe of the ammeter goes into that position. The tablet being used as a multimeter has the BNCs connected to the right side of the device. And so the display goes to show a fraction of a millimeter, 0.134 millimeter. Whereas on the digital multimeter we've been using, I don't have quite the resolution on this. This does not have a microamp scale. It has a milliamp scale, and its milliamp scale in this case happens to show me 2 digits after the decimal point. The tablet Oscilloscope multimeter shows me 3 digits after the decimal point, but I still have to convert this from millimeters into proper engineering notation, so it should be 134 microamps, 100.134 milliamps into 134 microamps. Well, interestingly enough, there's a little inset screen that appears on the lower left of your tablet oscope, and that inset screen does actually show the current in units of microamps. There's the U and there's the A, 134 microamps, which is really, really nice that it has this degree of resolution for an ammeter. And we calculated, if you look on the screen, we had actually calculated 130.93 microamps RMS. And keep in mind, both of these measurements on the digital multimeter as well as on the tablet in measuring AC, and you can see AC on this right here. This is not measuring DC, it has AC on the screen. And the same thing true here, this has AC on this screen. So it's measuring AC voltage in the form of RMS. Neither one of these is showing peak current. These machines are not designed to show peak current. You can see RMS current as we have calculated, and it shows up very, very nicely. Okay, so this is the current measurement of the tablet oscope. And let's go ahead and do this. Okay, my friends, now we're back to camera mode and just wanted to show you the Pico setup. So the PicoScope setup, this is their PicoScope Series 2000, specifically the 2204A, and very compact, as I showed you earlier in our side-by-side with the tablet from FNIRSI. So we have our channel A BNC connector, we have a channel B BNC connector, and we have the signal output BNC connector all fastened in place, ready to go. And then my circuit board, as we have set up previously, we have our signals coming in on the red rail. So I have one connection for my signal coming in, one connection on the red rail for my channel A reading. This particular green wire comes to the blue rail. So this is my alligator ground lead. This is the other alligator ground lead to my blue rail. The other probe is set up here. This will be my channel B. So this is what I'm going to be able to compare and see if I go to point A, point B, point C, whether these our predictions match our actual measurements on the PicoScope. The ground for the channel B, oscope lead to the PicoScope, is grounded here at point D. So we have this loaded presently. This is the jumper wire from the red rail to the first resistor, through the string of resistors down to here to the blue rail. So this is set up ready to go. And then I will then use this handy dandy wire jumper to just place where I want at different places in order to make measurements. And let me move this out of the way. That will be my point A. I'll just leave this one out here for the time being. And that's great. So if I wanted to measure at point A, I take this yellow jumper wire connected to my channel B oscope, and I will measure, boom, at point A. So this is my technician test point of voltage measurement, V at point A with respect to ground. My B at point A with respect to ground is here. My C at point A with respect to ground is right there. And my D is right here, which is basically ground. I should have a flat line on the oscope. So we will go ahead and leave this guy here at point B for the time being. I'll just leave it at point C. Actually gives me the biggest contrast of display going. And then what we'll do is, now that you can see the physical hookup, I will be switching verbally from A to B to C to D. So I'll be doing that verbally while you're looking at the PicoScope screen. So I'm going to switch to a share screen in just a moment so you can see the PicoScope. Okay, we are now looking at the PicoScope screen. Won't show you the download and the installation of the software. That's something that's fairly easy to do should you decide to invest in one. I highly recommend both oscopes that we're playing with today. But let's take a closer look at this particular display screen for PicoScope. So we have right now channel A controls right here. Channel B is off right here. My signal generator is set up here. So if I tap signal generator for just a moment, it comes up with its own dialog box in this inset portion of the screen. I can select the frequency. So right here, I can punch in 5, 6 hertz or 890 5890 megahertz. So I can select the category of frequency all the way into millihertzes. So I'm just going to do one, let's clear. And let's just do 1 kilohertz and call it a day, because that's the frequency that we've been using. So that's how we set the frequency. Now, amplitude is set up here. And again, I can dial in the specific kilovolt, volt, millivolt. I don't know why they have a kilovolt setting here. I have only had this unit for about 2 days and exploring it right now. And I think a lot, very highly of it, but we'll have to explore what this kilovolt thing is. I don't think this can kick out 1,000 volts. But in any case, I'll have time to explore that. For the time being, we have volt here, and we previously said 1.50 volts is what we're going to start off at. So 1 kilohertz, 5 volts, signal generator is on. I can turn it off. See there, it's off right there. And if I try running, I have flat line. So my running and stop button is right here. Run, stop. I've got no signal that the leads are reading whatsoever. So turn this back on, turn the signal generator plus to go on, and I can hit my auto setup button, let it do some thinking, and there it's got an auto setup, and presently it's set this up to show channel A, and I'm going to stop this and then do some adjustments and some things to play with. All right, so that having been said, let's bring in channel B, automatic there, let it run, stop, and interestingly, this on a voltage divider is going to need some fine tuning here. Be right back with you. Okay, so we're back on the share screen and we can see the PicoScope screen, and everything has now been set up properly with some adjustments. So I can play with the visualization of the trace on the screen. If I have not enough waveforms, I can have this in the run mode. I can have a whole lot. I can have less. I can have like one big one like so. And then I can look more closely at taking this apart, if you will. Let's go ahead, let this run, and let's go here. Scope 200 microseconds per division. Let's do 500 microseconds per division. Have it stop. Okay, we've got plenty of peaks to be able to see what's going on. And let's go ahead and see where we are. Let's go ahead and bring this cursor down and run it to the very tippy top of this. And we can see, oh, that's interesting. My generator shows over here, I've got 1.5 volt peak coming out, but my signal generator, the oscope lead on the board, because this is a loaded circuit now, is not showing me close to the 1.50. This is that loading effect I said that could occur. And so if you see this right at the input, because channel 1, this dark blue trace, is, or channel A, is my input, this is directly hooked up to the signal generator. If my signal generator says it's supposed to be putting out 1.5 and I'm not measuring 1.5 on the board, then we need some compensation. We talked about that before. So the first thing before I go comparing any wave shapes is I've got to get my V peak on my input to be accurate with respect to the design parameters. So the design parameter specified I needed 1.50 volts at the peak. on the board, and I'm not getting that. So what I need to do is come here, play with my signal generator, and I think we played with this before, said that this should be about 1.67. Let's see, 1.67. Let's see how close we come. And let this do a run. And I hit a pause. Aha, you can see it's just a touch bigger. So let me grab the cursor, which is this blue arrow here, and bring my mouse over. The mouse changes in such a way it allows me to grab this. I now pull it up to the tippy top of this wave, and a little bit of fuzz there. So get this as close to the top without the fuzz as much as possible. And it looks like I'm just a little bit over. So let me bring this down. So let's go and make this 1.62. And I'll let this run again and stop. And now bring this guy down to the tippy top. Okay, I can fine tune this a little bit more. Let's make this 1.65. Split the difference, let it run, and scooch this back up to the tip. Right there. Okay. All right, that's as close as I'm gonna want to get to this. I've got 1.512, so I'm 12/1000th of a volt higher than my desired 1.50. Good starting point. If I dink around with this and spend some time, yes, I could probably get it to 1.500, but not worth the effort. The important thing is to see how these waveforms contrast with each other and see if the channel B is coming in where it ought to, okay? So let's go ahead and take a look at channel B. Now, channel B is right here in red. It shows B, and it shows that I'm at the 100 millivolt per division scale. And so 100 millivolt per division scale, let's take a look and see where this guy is at. So I'm going to grab this cursor, bring it down, and we are at, let's go ahead, run, stop, and check. Okay, let's talk a little bit about troubleshooting, because we anticipated at point C something in the 300 millivolt peak range. So if I grab my red cursor and put this to the tippy top of the red waveform and see what my display shows me, I'm at 37.4 millivolts. Now, wait a minute. Something's wrong with this. It should be 370 something millivolts. Why is it at 37 millivolts? Well, nothing wrong with our display, nothing wrong with our hookup. What is wrong is the probe itself. Your Oscilloscope probe has a slider. We talked about this quite some time ago when we looked at leads on our machines, and the Oscilloscope probe has a slider switch. You slide it in one direction and you get what's known as a one-time reading. You slide the slide switch into another direction, you get a 10 times. So right now, as I'm looking at the Oscilloscope probe on the board, it is on a 10 times. And let me go to pause this and show you on the camera what it is. All right, so this is actually a pretty good view of what it is we're concerned about. See, this slider switch is the one I'm talking about, and it shows 1x on this side, which is the normal function, and it shows 10x on this side, which gives us a different degree of sensitivity on the Oscilloscope probe. So what I need to do is to slide the slider switch from the 10x position into the 1x position like this. You should check with all of your probes before you go to make the connections and make sure that this is set up properly. So 10x is over here, 1x is over here. Haven't used this particular probe, but just received it. And that is a good reminder for myself to make sure that this is in the 1x mode. Now, once I set this in the 1x mode, everything will be hunky-dory on our Oscilloscope reading. Since this happens to be on the view screen right now, let me talk about a couple of things. Your Oscilloscope, whichever you purchase will come with colored rings. So the colored rings you can snap on. They have different color rings. You can snap on the probe itself, and the same color ring can be snapped onto the BNC end. So you can just look on but either end of your probe cable and by the color and know which channel you're plugging it into. So that's what the color there is for. The slider here, the ground connection is on a swivel. I can move this around as necessary to get the right angle of the ground lead to where I want it to be. Let me raise the camera just a touch here. Okay, show you some other aspects of the probe. This is set up with the mini hook. So that means if I go to squeeze this backwards this way, it will release the hook. You can see I've got a little, oops, hook action right there. If I squeeze, a little hook comes out, and I want to pop this in place like so, and it grabs onto my jumper wire. Now, separate of this, if you wanted to use this similarly in a fashion to your digital multimeter with needle probes, this is very simple. This just pops off. It's a little stiff. Okay, a little too stiff to be popped off. So well, that was very, very tight on here, but it is designed as a pull off. And as a pull off, this will reveal a needle probe. And so the needle probe is designed such that you can go right down onto a particular pin of a chip and be able to read its waveform right on the end of a chip device because this is really, really tiny, gives you a very precise point measurement of whatever it is that you would like to connect the Oscilloscope probe to. And be very careful, this thing is sharp. There is a protective cover that covers this. And so here's a little colored, the protective tip that we're talking about. So if I were to use this very frequently, but when not in use, because this mini hook end is so hard to pull on and off, I may choose to just put the little protective cap on. It snaps in place, and that will protect it from damage. You can also use this part way as a protector, and then you can also use this as an insulating device. So there are caps that you can put on that will cover this completely. And in this particular sleeve is designed such that it will protect the metal parts from accidentally touching some pin that might be next to it. The colored rings are shown here, so you can put on different color bands onto your oscilloscope ends to more easily identify them as you plug them into a variety of different oscilloscope BNC inputs. Okay, so this is another view of the setup. I've got my channel A BNC with a yellow ring. I've got my channel B BNC with a little pink colored ring, and I can tell that easily on both ends because I put the little color band on the probe as well as the B and C end. So I can tell just by looking at the band that this is the channel B because that's what I've set up on the other side. Now, what we're also going to set up is the little jumper wire that we will be connecting. And so when I will be calling out point A measurement, I will take this little jumper and go to point A, and then go to point B, and then go to point C. This will be what I'll be doing on the board with this particular end. It's connected to my mini hook over here. So by having this on a flexible, longer piece of lead, I can very quickly make point measurements with respect to grounds. I'm just going to bury that there for the time being, and now we'll switch back to screen mode. Okay, so back to screen mode. I hadn't changed anything on the screen. It was stopped previously when my probe was set in the 10x position. So in the 10x position, this was reading the waveform at point C as 37 millivolts instead of 370. So now when I run this, this should show correctly. If I change its input, Also, if I have a better connection. So let me make sure my connections are good. So another good troubleshooting step, and that is what happened to our waveform. Our channel A waveform, 2 volts per division. I'm coming in at 1.52. My channel B waveform is really an ugly looking thing. So we need to check our connections on the board. And as it turns out, in my last frame of the board, I had pulled the channel B yellow jumper. Oh, I planted it somewhere else on the board other than point C. So I'm going to reconnect this at point C and now run this. And in the run mode, hit stop, and you can see, oh, my red traces come on beautifully. But lo and behold, I don't see the top of it. Why don't I see the top of it? Because my scale for channel B is set to be too sensitive. Each division is 100 millivolts per division. So I'm going to run this and I'm going to change this by hitting plus, 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 and that brings the waveform down. If I leave this here at 500 millivolts per division, it looks like pretty much the same size as my input. And we know that can't be. If I go to slide this guy up to the top peak here, yes, we're reading channel B, the output in your voltage divider at point C. We're reading this as 369.9 millivolts. That's pretty spot on to our calculations. And even though it looks, the red trace looks like it's almost the same size as the blue trace, they are different values. Why? Because I have my voltmeter settings on different scales. The channel A is on 2 volts per division scale, whereas my channel B is on 500 millivolts per division scale. If I go to change these to be the same scale, from 500 millivolts to 1 volt. If I go to change them to be the same scale and I rerun this, you will see the waveform come into play. So I go back here, they were almost the same, and I change 1 volt, 2 volt, run, stop, and this is now on the same scale. They're both at 2 volts per division, and it goes to show my red trace is quite a bit smaller, which is what we had calculated it to be. And there, if I bring my cursor down to the tippy top of the peaks of the red trace, I can see I've got 368.6 millivolt peak against my 1.5 12 volts peak on my input, which is great because if I go to compare this with our values right here, my point A was 1.5 volt peak, and my point C, 370, is pretty close to my 360 millivolt peak on my oscilloscope. So now what I'm going to do is I'm going to switch back to my PicoScope, and now I'm going to switch the probe from point C on my voltage divider to point B. And there, now it's at point B. I will run this and you'll see the two wave shapes be much closer to each other, but not identical. Pause. And you see they're much closer to each other. They're not identical. We don't expect them to be. We expected a slight difference between the input at point A and then the voltage at point B should be slightly less. Let's go ahead and move this up and see what we have here. This is reading at 1.301 volts peak according to this. Same scale, 2 volt scale, 2 volt scale for both A and B. And my rulers are showing, and I can move the ruler around anywhere that I want. I just happen to have planted it up there. I can move it over to here, let it go. All right, so my point B voltage measures a peak of 1.3, and my right here, 1.3, 1.31 volt peak. Pretty sweet. So the O-scope shows very nicely the 1.5 volt peak at point A, the 1.31, we calculated 1.31. The scope is showing you 1.30 at point B. We calculated 370.37 millivolts peak at point C. And if I bring this back to point C, there's point C. Hit the run, stop, and bring my cursor back down. I can go to either. I've got a little flatness there. I'm going to go to this particular one. So 379.4. So every once in a while, if you get on your trace, the way it draws this out, if you see a bit of a flat spot occur and you want to read the peaks as accurately as possible, there's no reason why we couldn't go to the negative peak, because the negative peak is the same as the positive peak, except it's in the negative value, meaning it's below the 0 volt. Here's the 0 volt reference line. If I want to set this to the positive peak, I will go to the one that actually doesn't look like it's flattened out, and that would be right about here. This one right in the middle, and I'm reading 374 millivolts peak at point C, and my calculation shows 370. So pretty darn good. All right. So all that being said, let's corral a moment and do this. Go here. Okay, we did the measurement of currents. I won't be measuring the RMS values on the digital multimeter because that's pretty academic. The point of this exercise is really to show you the comparison between the two O-scopes, which I think have been pretty thoroughly demonstrated for this first time comparison between the two. There's many more features to both scope machines, but for the purpose of this initial comparison, I think we've covered the most important points of interest to the beginner electronics technology, electronics engineer individual. So that being said, which way do you lean? Let's take a look. I did make some suggestions at the end of our previous AC Oscope AC-1 training, and I made some recommendations. The Pico is shown here, the 2204 that includes the leads. Very nice test leads and the power cable, and the software is free, and the latest software is PicoScope 7, which is very comprehensive. You saw it demonstrated, and at present it comes in at about 165. The link to this is in the description of my YouTube. I am also using this unit here, the FNIRSI, the 2C53 unit, and this is the 4.3-inch screen, and at present this is running about 139, a little bit less than this by about $25 or so. And between the two that I compared and contrasted, which would you pick? Well, there's a number of considerations that we'll talk about in a moment. I did also show this, and I've got a shout out to a retired colleague of mine. Retired colleague on the YouTube goes by Taxi Neil 1. So hello, Taxi Neil 1 in the UK. He's retired, as I am, and we needed mental stimulation. So he got into repairing electronic equipment as a hobby, and he acquired this unit right here, which is a fascinating little unit because it is more compact than the 4.3-inch screen. It has a 2.8-inch screen, which the bottom line here is this is even more compact. This has the size and the handle and the handling, the feel of a digital multimeter because the connections are right up in front as a typical multimeter are. What I like about this is this has 3 full-size BNC connectors, which is really rugged, really stout. The one that I tested has 2 BNC, regular size BNC connectors, and then that micro connector that I was a bit concerned about fragility because it's non-standard. But this particular guy here has 3 full-size BNC connectors, so very stout. And all you really want in the portability end of things is to be able to just compare screens. Okay, compare the wave shapes. What does wave shape A look like with respect to wave shape B? And depending upon what you're diagnosing, all you need to do is really see and maybe get some readings, which the unit's very capable of, and its price point is certainly very attractive. Then we go on to another brand that is a 3-in-1 smart scope, and it comes in at the same price as the FNIRSI one that I tested, but a little smaller screen at 3.2 inch diagonal. Does have a multimeter, and it does also have signal generator as well as Oscilloscope. So what it comes down to, different size screens. Now, the considerations that you have to think about are this. Bottom line, which would you choose? If you don't have the budget for a full benchtop rig, like I have set up in my man cave, for Oscilloscope and signal generator, then let's look at the important highlights. The compactness of the FNIRSI and other handhelds is very attractive because much lower cost, the budget is always a concern, very portable, very compact, occupies little desk space, does not require a PC or a laptop, so you can use it independently in your hand in the field a lot more easily than schlepping a PicoScope with a laptop around with you. One piece of equipment is always better than schlepping 2. But again, it depends on your application, what you're trying to measure, and how much information you're looking for. Then some of these tablet and handheld units may have a bonus digital multimeter built in. That's nice because that, again, eliminates one more piece that you have to schlep into the field. So that's a very nice consideration of the FNIRSI that I tested. And let's take a look at some of the highlights of the PicoScope. The PicoScope is very attractive for much larger screen size capabilities. And I put down here for us myopically challenged users. I have cataract surgery coming up. I've had 1 cataract surgery done, not quite where the vision needs to be. So for me, bigger screen, more information on the screen, the better for my eyesight the way it is now. The PicoScope also, because of its software, has way more controls of the functions and way more details in the results. I repeat, this is not vendor sponsored. I paid for these units out of my own pocket. I own these units and I'm not swayed one way or the other. So let's look at some further considerations. Portability versus size. What's your priority? Your priority, okay? So here I've got a 4.3-inch tablet screen in comparison to a 16-inch laptop. Which do you prefer? I prefer both because they're really quite different. One gives you portability and the other one gives you bigger screen. So here's a 16-inch screen in comparison to this. And sorry, this is washed out because of the contrast of lighting difference between the two, but the resolution is very, very good, as you saw demonstrated earlier, but not in the photograph on the camera. Let's go here. All right, let's compare the 4.3 to a 20-inch monitor. So there's my same 16-inch laptop here. The 4.3 is in the center, and I've got a 20-inch monitor over in the side. So I've got even bigger screen capability. Again, I vote for both because they are used differently. Now, over here in my man cave, I've got 3 scopes set up. I've got the 4.3 in the center right here. I've got my bench oscope on the left side. I've got my laptop on that size screen, the 16-inch, and I have this hooked up to my 46-inch monitor. It's a television monitor, so even bigger. And if you're not satisfied with 46, sky's the limit. You can project this out to 10 feet wide if you want. This is in my den, so here's my 4.3 against a 16-inch laptop against a 60-inch monitor. I vote for all of them. Again, it depends on what it is that you are using this for. So to close, my friends, here are some suggestions. And for each of these suggestions, the affiliate link is in the description of my YouTube. If you've liked the information that I've shared with you so far in terms of circuit analysis, calculations, circuit board building, measuring the quantities on the scope with test instruments, and then as well as the initial comparison between a PicoScope and the FNIRSI tablet. If you like all of this, then please give us a thumbs up and subscribe to the channel. And when new things happen, you'll be alerted. I hope that that's the way YouTube works. Yeah, I thank you all very, very much for your most kind attention, and I look forward to sharing future videos with you. So for now, sayonara, adios, adieu, auf Wiedersehen, and we will see you again next time. God bless you all.